Well, as we have mentioned in our previous discussions of scalar and vectors and also in vector subtractions, we have mentioned regarding the concept of algebra of numbers, algebra of scalars, algebra of vectors, algebra of tangents. We have also the algebra of phasors. We will have a brief discussions of the algebra of phasors, looking to the importance of phasor in various parts of the physics, like in analysis of AC circuit, in oscillation and waves, in your optics, electronics, molecular quantum mechanics and condensed matter physics and many other parts. Phasors are sinusoidally time varying complex coplanar physical quantities. Now sinusoidally, as because if you see it rotates, and complex it is because we use the property here, that is square root of -1 as the j, and coplanar it is because the discussions of all these phasors are on the same argand plane we will be looking into. Now coming to the properties, j square, which we say that j equal to square root of 1, j square we will be taking as -1, and j square times phasor A will give you the inverted phasors, means minus A. If A is the phasor, j square A will be minus A, and j to the power 4th A equal to A, simply j 4th being 1, so therefore j 4th times A will give you the phasor itself. In Cartesian form, if you write the phasor as capital A equal to small a plus j times B, with the small a as the phasor component as along positive x-axis, which is the reference axis here, and small b as the phasor component along positive y-axis, where we can reach from the reference axis in moving 90 degree in anti-clockwise manner. If we are considering the anti-clockwise, it is 90 degree, or 270 degree if we are moving in clockwise. Polar form, you can write this phasor A equal to A cos theta plus j times A sin theta for anti-clockwise rotation of phasors. And if you consider for clockwise rotation of phasors, this phasor A can be written equal to A cos theta minus j A sin theta. With A cos theta, A sin theta here are the corresponding phasor component along x and y axes respectively. Now here cos theta plus j sin theta, which you see, it acts as a operator to rotate the phasor A by certain angle theta in anti-clockwise directions, which is we consider from initial reference axis, and the reference axis here is positive x-axis. And similarly, your cos theta minus j times sin theta, it acts as an operator to rotate the phasor A by angle minus theta in clockwise direction from initial reference axis. And if you write in exponential form, the phasor A can be written as equal to A e to the power plus or minus j times theta, where A is the amplitude part and e to the power j theta is the exponential or the phasor. These can be written as for anticlockwise equal to A cos theta plus j A sin theta, and for clockwise you can write it as A cos theta minus j times A sin theta. In compositions of phasor, when two phasors are added or subtracted, then the resulting is a phasor whose magnitude is equal to the measure of diagonal of parallelogram formed with the component phasors as the sides of the parallelogram, and the resulting phasor angle is the angle made by the diagonal with the initial reference axis. Here the reference axis is positive x-axis. And for subtractions, the phasor to be subtracted is rotated by 180 degrees. Now for product of phasors, unlike dot and cross product that we have used for vectors, in product of phasors, the resultant is a phasor having magnitude equal to the product of magnitude of the component phasors, and the resultant phasor angle is equal to the algebraic sum of phasor angles of the component phasors with respect to the same reference axis we have started. For division of phasors, as a part of the quotient rule, you can write the resultant is a phasor having magnitude equal to the ratio of magnitude of the component phasors, and the resulting phasor angle is equal to the algebraic difference of phasor angles of the component phasors with respect to the same reference axis. So therefore, accordingly, we can write down AB equal to e to the power j times theta A plus theta B within bracket, or A by B equal to A by B as the magnitude part times e to the power j times within bracket theta A minus theta B. Ranging power of phasors. If we multiply a phasor n times, then the resulting phasor can be expressed in accordance with de Moivre's theorems, which can be written as an equal to a to the power n as the amplitude part, and e to the power j times n theta, which can be extended as a to the power n times cos n theta plus j times a n to the power sin n theta by de Moivre's theorem. And we will extend our discussions using these phasors in our further discussions. Thank you.